PID Controller. A proportional integral derivative PID controller is used as a feedback control system in industry, which is usually used for temperature, flow, speed and pressure control. Let's see the characteristic graph. Number 1, proportional control. Use for immediate fast response, which generates output directly proportional, but disadvantages were high overshoot. Also it takes a long time to stabilize. Number 2, integral control. Directly stable at the end, but there was a low response, which takes a long time to increase. Also got steady state error. Number 3, derivative control. Not too fast and not too slow, but it mainly functions to reduce overshoot and improve stability. With a combination of P, I and D, this is gonna make the response become a fast time response, no overmove, which is overshoot and stable control. This is the structure that we use for open loop simulation, and this is a closed loop structure for simulation. Now let's see the difference between open and closed loop. Open loop got no feedback and the closed loop got feedback. Feedback is gonna respond back to PID after reading the output. Then the PID controller is going to regulate the value until it reaches the set value. This is a structure for a closed loop which contains KP, key and KD for PID controllers. Then this is the result for the proportional controller. Based on the structure block diagram, P got input which is 3, I and D are 0 values, which will give results for proportional data only. So the graph shows unstable results and takes time to stabilize. Also got spike overshoot, but what is good is, proportional give output directly proportional and fast response. This is a combination of P and I which is proportional integral. KP input is 1.5 and KI input is 5. The graph shows unstable results take longer time to stabilize, which shows the function of I is to reduce the speed of the output. Also this graph got overshoot, but stable data at value 1 when using this value for the combination of P proportional and I integral. The combination of P and D which is proportional derivative. KP input is 65 and KD input is 10. The graph shows results highly stable and no overshoot, but got a steady state error when using this value. Also can see that D derivative function to reduce overshoot. This is a combination of PID which is proportional integral derivative. KP value is 4, KI value is 10 and KD value is 0.5. This graph shows the result is highly stable and reduces a lot of overshoot. Also removes steady state error. This is data comparison for the PID controller. Now let's find which characteristic is the best in this table. We know that steady state error gives bad data results. Since 0.75 and 0.98 got steady state errors, remove P and PD. Now left PI and PID. Both steady state are good. For maximum overshoot, PID won and got the least % overshoot. For response time, PID won because it got 1.3 seconds which is faster than PI for settling time. PID wins because it takes less time to stabilize the data. This is part for PID tuning. For this part we set tuning for the P proportional controller. Then we got this proportional result, which is high overshoot, steady state error and takes time to stabilize. We get value P about 1.77 on the tuning. For PI proportional integral, we set this PI block diagram. Then we get this PI result which is less overshoot and disadvantage as it takes longer time to stabilize. Tuning result for P is 0.67 and I is 2.72 for the PI. For PD proportional derivative, we use a PD block diagram and tune it, which got results for PD and show that this is the most stable for PD graph when tuning. Also the graph shows it has steady state error, but it takes less time to stabilize, which makes the tuning result for P is 1.86 and D value is 0.05 result. For PID proportional integral derivative, this part is gonna change into PID devices. We get the best tuning result for this diagram. The tuning PID already makes the graph reduce overshoot, no steady state error and fast time response. This is data comparison for the PID tuning controller. Let's find the best characteristic controller in this table. Peak is steady state value. Remove P and PD since they have less than one value, which is steady state error. Now left PI and PID. PID is the best characteristic because it has less overshoot and fast settling time, which is better than PI.